Good.
Okay. Great. Thank you for the kind introduction. Thank you so much for having me today. I'm very excited to share some more recent work on 4D digital twins from videos in the wild. Okay. So if our goal is to capture reality of our world, how should we do this? Now, traditionally, there are a few ways. So one way is that we can have graphic designers to design the models, but that's going to be very time-consuming, and it's going to be a lot of manual work. Alternatively, we can have specialized capture system like this scan break, but it's a control setting and it's very expensive. So both can produce very high-quality output, but they're not really scalable. But our visual world is such, so incredibly rich that we really want to be able to capture reality at scale. So how can we do that? Well, everyone has a phone, which always comes with a camera. And we can very easily record our lives just by taking videos. For example, here is a video taken by me while walking through a local market. Now, if we can capture reality from such everyday video, then that's going to be much more scalable because it's very easy to record a video, and there are already a lot of them on the internet, and they keep growing, right? So why in videos, not images? Because our world is moving. There's it's only possible to capture the dynamic world if we capture things over time. Okay, to be more concrete, what is the problem here? So the problem we're tackling is 4D reconstruction. Specifically, given a monocular 2D video, we want to recover the following things, which involve solving an inverse problem. And the first is the camera parameters, which involves both intrinsics and extrinsics, or how we are software moving in the world, and also the scene geometry of the structure of the scene at every time step. So something is happening here. And also the 3D scene motion of how things move in 3D space over time. Now, this is a very challenging inverse problem, and I will walk you through with a cartoon animation to illustrate why this problem is so challenging. So our underlying 4D world has the following component. We have the static 3D environment, we have dynamic 3D subjects, and us as observers who are also moving in the world, right? Now, at every time step, we get a single 2D projection of the 3D world, which means that we lose an entire dimension. Now, everything is flat. There's not really a direct way to tell how far things are. And this is also a partial observation because we only get to see the world from a specific angle with a limited field of view, and there are also occlusions in the view. Now, we might want to just see more by moving, but the thing is that the world is also changing at the same time. And that will give us a different 2D projection for the current time step, but both the world and our perspective might have changed. So moving objects is really a big headache because we can't really get multi-view observation of the same underlying geometry for a specific moment, where if we only have a single camera, then we're bounded to only have a single observation for each time step, and because the world is changing. So these are the input to the system, and we want to really solve this inverse problem of getting the camera parameters, the geometry of the scene, and also how things are moving in the world. So this is very challenging, and it wasn't possible until very recently. So I work on this specific problem myself, and here's our kind of input and output. This project is called Shape of Motion. So from a single casually captured 2D video, we can recover the quantities that I just mentioned in this project. These are all cherry-picked results, and but this is something that wasn't possible before, especially from casually captured the video. And similarly, there are many other work that came out around the same time that addressed basically the same problem with somehow similar approach. So the question I like to ask here is basically, what make this 4D reconstruction possible? Because it was really difficult before. Now, I like to reflect on that, and I think there are two very important reasons. The first is that we made a lot of progress on differentiable rendering and scene representations, which makes it possible for us to optimize a scene representation effectively from image observations or information in image space. And specifically with 3D Gaussian splatting, it is very compatible and friendly with motion. So that's why things start to work. But that's only part of the reason. Now, another very important reason is that there are a lot more very powerful data-driven priors that we can leverage. So in our project Shape of Motion, we leverage a lot of 2D domain priors like geometry and 2D tracks. And those are just very, very important to make the system work. As I mentioned, this problem is such a kind of ill-posed problem. So you do have to bring in a lot of priors to solve the problem. So this is, I think, is really important for us to keep improving our ability to capture the dynamic 3D world or the 4D world. So that's what I'm going to talk about today. I'm going to talk about some more recent work on learning priors about the 4D world. So first, I will talk about a continuous 3D perception model that learns priors about the geometry and also camera parameters from just RGB videos or image sequences. And the second part, I will talk about the simultaneous reconstruction and tracking method that jointly learns about geometry, camera parameters, and the scene motion. So I'll start with the first one. So just to give a little bit of background, our work follows Duster, which is a very exciting recent work that learns very powerful priors about the visual world. Now, it's really cool to me because it's an end-to-end pipeline, effectively doing both structure for motion and multi-view stereo without relying on the old pipeline. So it's completely a new paradigm. And also, it's a very large-scale training paradigm, to the time that it came out. And because it is, learns a lot of priors, it can solve very challenging tasks. Like in this case, even the two views are not really overlapping, you can still reconstruct the scene, which is very challenging for traditional methods. So this is really exciting progress, but we're not done yet. So there are still a few challenges. The first challenge is that Duster is a pairwise paradigm. So it doesn't really natively support multi-views or videos. If you have more than 2 views, you have to use additional procedure, which is global alignment, to align them into a shared coordinate space. Now, it also doesn't really have a focus for dynamic scenes, because the training data is primarily static scenes. And third, you can think of it as offline if there are multiple views, because you need the global alignment. And global alignment is an optimization process. It requires having all frames at once, and optimization also takes some time to finish. So in this work, we try to address these limitations. So our work is called QTR, which is short for Continuous Updating Transformer for 3D Reconstruction. And it really has a focus of being able to do online and being more flexible and general. So here are some properties of our work, which I'll introduce more later in the talk. So first, they can accept a variable number of input images, not just a pair, but it can be a single image or more frames. And it works on both static scenes and dynamic scenes. And most importantly, it can run online and it can update continuously. And we really want to emphasize the third point because, in order to interact with the physical world, we do need to update and, be able to function online, like what actually in real time, this is what the bat is doing here. So I don't know if you can see it, but basically, in a lot of scenarios where we need to be able to create a digital twin in real time, right? So how do we achieve this? The key idea is very simple. So we need a big neural network, store the data-driven prior about the visual world. But more importantly, we also have to maintain a state that captures the context of the specific scene we're looking at right now. And as you get more observation, we should be able to update the state using the new information. And this is going to be an online and ongoing process. Okay, so more concretely, our method works as follows. So at the core of our method is a state, which is a latent C representation parameterized as a set of learnable features. And when an image comes in, it will be encoded into a set of image features. And then the state and image features will talk to each other in a joint process of state update and state readout. And this part is implemented as two interconnected transformer decoders, which is very similar to Duster. So the state update decoder will update the state using the information from the image features. And at the same time, the state readout decoder will read out information from the state to augment the image features, and then output explicit 3D content. And in this case, it includes the point map, similar to Duster, and also the camera pose. So the same procedure just repeats. So image comes in, talk to the state, and update the state, and read out output for the existing current observation, and so on. So this formulation is very simple, but it's also very flexible because there's really no constraint to what the method can handle. So we can train it to handle both static and dynamic scenes, and also both continuous video streams and unstructured photo collection, which we'll show results on later. Now, so how does this compare to Duster? So there's a very intuitive way to contrast the two architecture, which is that you can think of Qt as replacing one side of the transformer decoder with this persistent state. So basically, Duster works on a pair of images, but Qt has a state that contains all previous contexts. And this simple change allows it to handle a flexible number of images, and also being able to update online, and also being able to incorporate longer context. Okay. So a very interesting question is, because we have this latent state for the C representation, what is really inside the state, right? This is a latent representation. It's very intriguing to understand it. So here we design a mechanism that allows us to read out information explicitly from the state. So here we also allow the state to interact with a virtual camera query. So it's just basically a camera parameter for both intrinsics and extrinsics. And then we're going to read out from the state for this query camera what the point map will look like from that viewpoint. Okay? So what will happen is that we will first turn the camera parameter into a dense remap representation, which is just a 6-channel image that encodes the ray origins and the redirections. And then we're going to use a different remap encoder to encode the information of the remap. And then we're going to use the same architecture that I just introduced to read out information from the state. So basically, everything after the encoder are shared for both the images and the remap. And this will allow us to get a point map for the query camera, which represent what the model think could have been there for the query viewpoint. Now, if we add it back to the existing reconstruction, you can see that it makes the reconstruction more complete, because here is empty, and the inferred point map can really complete it, which means that the state contains information not just for regions that are visible, but also for regions that are beyond observation, which means that it encodes rich information about 3D scenes. Now, of course, this is not an emergent property. In order to get this result, you also have to train the method specifically to operate with the remap. So in other way, you can think about this camera query or the remap as a way to both probe the state to understand what's inside, and also a way to enrich it through training, because if we have to add any supervision, then we have to have explicit content, and then that will propagate back to the state to enforce it to incorporate more richer information. So a tiny detail is that when the input is remap, we don't update the state, because technically the remap doesn't, or the camera query doesn't bring in any new information. It's just a way to understand what's inside the state. So that's basically the mechanism. Here, let me talk about training. So in order to incorporate useful priors, we do have to train it on diverse data set So here we actually process 32 data sets of very different scenarios: static, dynamic, indoor, outdoor, or real and synthetic. And we also released the processing code if people want to use our data. So during training, we'll feed in a mixture of the images and remap into the model. And we will unroll the sequence to get a prediction for each. And then we'll add a regression loss similar to Duster to supervise the model. Now here, the way to think about it is that you can think about remap as some kind of masked image. So it's, at a high level, conceptually, it has some similarity to masked autoencoder or MAE, because you can think of that as kind of masked token at the image level, and that enforces the state to capture, richer information about the scene, right? Okay, so and this will train the method to not only be able to do reconstruction, but also infer new structures. And here, let's look at some results. I'm showing the online reconstruction results of our method for static scenes at 2 different viewpoints. And this works for various environments and also different camera trajectories. And it also works for dynamic scenes. And here is a feed-forward or online reconstruction for dynamic scenes with both camera parameters and the dense scene point cloud reconstructed. And this is an example with large camera translation. And dynamic scenes are going to be fundamentally challenging for traditional methods, which do not learn any data-driven priors. And with large-scale training, the model also generalizes pretty well to novel objects and scenes, like in this case with monkeys. So not just that the method works on continuous video streams, it also works for unstructured photo collection, which might have a small overlap. And on top of the reconstruction, we can also try to infer new structures. And this is an interactive demo where we just take the reconstruction from the previous example, and we ask the model to infer the point map from a selected viewpoint to fill in the holes in the reconstruction. So here, as you can see, this makes the reconstruction more complete, which means that the model learns to infer about the structure of the scene, thanks to the data-driven prior that it learns. And this is also a useful way to probe and see what's inside the state. Now, to wrap up, this is one last example that highlights the model's ability to continuously update. Now, when we look at this image, I believe that we'll all think about it as a 3D chair, right? But okay, as I play this video, then your understanding about the scene must have changed, because it's not really a 3D chair. It's a visual illusion. It's actually a 2D plane. Now, this process shows how our understanding about the visual world can continuously update based on new observations. So the question is, can our model do something similar? So here, let me show our results on this sequence. Now, when the model only have access to just the first view, it understands it as a 3D chair, just like us, because this is the prior the model learns from the data. Now, when the camera moves to the side view, it becomes evident that this is actually a 2D plane. So the question is more about what happens at the end of the video, where the camera viewpoint returns to something closer to the to the initial viewpoint. So as you can see, the model maintains the understanding that the scene is flat, which is the correct interpretation, because it means that it is able to take in the observation and update its understanding of the scene. Now, we didn't train the model specifically for visual illusion. This is just a natural outcome of our training that enforces the model to learn to update. And it can do so even when the observation is contradictory to the embedded priors, like in this case. Okay, so to summarize, QLEAR is an online 3D perception framework that learns priors from data. And it learns to update continuously. And it also supports a wide range of geometric tasks. And this is a very exciting problem, and we're not the only one exploring it. In fact, there are many papers, even at this CVPR, that are tackling similar challenges. And here we're highlighting, a subset of recent work that, just to give a sense of how they work on different settings and have different characteristics and trade-offs. Now, these are all very exciting, and we're especially excited about our setting because we believe that for intelligent systems to operate in the physical world, they need to be able to process streaming data, just like how we are doing it. And it's also important to compress because eventually we'll need to be able to handle a very long context and continuous video input. So our method also have a few limitations. So first, training is slow because it's a sequential, training. You have to unroll the sequence, so we have limited parallelism. And also drifting and performance degradation is also possible on very long videos because we can only train the model for a certain length, and it doesn't really generalize out of, that much out of the training length that we have. And lastly, there is really no explicit modeling of scene motion, right? So we're predicting the geometry and the camera motion for every time step, but we're not really answering how things move over time. So that naturally leads to my second part of the talk, which tried to do a simultaneous reconstruction and tracking that learns about geometry, camera parameter, and scene motion jointly. So specifically, given a monocular video of a dynamic scene, so the method StarTrack produces this following output, which is not just reconstruction, but also tracking, as you can see from the point tracks. It's 3D point tracks in the world. So how does StarTrack work? Let's first recap what Duster and Monster are doing. So Duster is primarily trained on static scene, but Monster shows that as long as you fine-tune it on dynamic scene, the same architecture also works for dynamic scene. So specifically, for Duster and Monster, they're predicting the following things. Now, for the first branch, you're predicting the point map of the first view's content in the first view's coordinate frame, and also at the first view's time step. Whereas for the second branch, you're predicting the point map for the second view, but in terms of coordinate system, it's aligned with the first view's coordinate system because you want to reconstruct things in a shared coordinate frame. And you're still, in terms of time step, predicting the current view's time step. So basically, the two time steps are not aligned, and that's why there's no tracking component because they're not really trying to align or move things from one view to the other time. So StarTrack made a very simple conceptual change, but suddenly allows the same architecture to also perform tracking. Of course, you need to train the method to do so, but the conceptual change here is that for the first branch, we're going to predict the point map at second frame's time. Okay, so how does this work? So let's consider the case where you have a video. When you have a video, the first branch, we always take in the first frame. And then for the second branch, we're going to iterate over the entire sequence. So the second branch sees the second frame until the end of the sequence. And now you can see how the first branch can do tracking because as you alternate the second branch input, you're predicting the same content in terms of the points in the same coordinate frame, but changing the time. So basically, this gives you the flow of how the points are moving over time. And so basically, the first branch is doing this kind of long-range, dense point tracking in the world. And the second branch is unchanged, so it's doing the same thing as Duster and Monster, which try to do this dynamic scene reconstruction. So the first branch, we repurpose it as a tracking branch, and the second branch is the same as Duster and Monster, which does reconstruction. And we're going to train both because it's a repurpose of Duster's architecture. And more specifically, we'll initialize the weight from master because we want to reuse the priors I already learned in master about the structure of the world. But we're going to fine-tune the architecture on two synthetic data sets with 3D point track annotation. So that includes the point odyssey data set and also dynamic stereo data set. So both comes with annotations for the 3D point tracks in the world. And because such data set is so scarce, we also have a mechanism that allows us to improve the performance on a specific test video at test time through some kind of test time adaptation. So we're able to use reprojective supervision signals like 2D trajectories and monocular depth map to fine-tune the network architecture on a specific video using some off-the-shelf methods. Okay. Now, it turns out that this kind of dense 3D tracking in the world coordinate space is not really studied as much in the past. So we also propose a new benchmark called world track to evaluate world coordinate tracking and reconstruction. So here are just some qualitative results. Here you can see there are actually 2 point map, and one is the first branch that's tracking, and the other is the second branch that does the reconstruction. And that gives you both the reconstruction and the point tracks. Okay, so just quickly summarize why do we want to work on Star Trek? So first of all, this gives the ability to do 3D point tracking in the world, and it's a unified framework that gives you both the geometry and the motion. And it's also very simple, right? We're doing a very simple change, but this allows us to represent all of the major kind of components of the scene in terms of geometry, camera motion, and scene motion. Okay, so there are still a few limitations. First, as you can tell, there really isn't any temporal context modeling, right? Because the input to the system is always just a pair of images. That makes it struggle at handling large viewpoint changes or very complex 3D motion. And secondly, as many other 3D learning framework, we still largely rely on data sets. Now, in this case, 4D supervision, but such data is very scarce, and we need to explore ways that we can train the method in a much more effective self-supervised way. Okay, to quickly summarize, in this talk I talk about 2 work for 3D perception and joint 4D and reconstruction tracking. And they share some common properties of being feed-forward, end-to-end, and more importantly, data-driven. And there's few, I think, very exciting directions for 4D digital twins. So first of all, I think tracking is still something that we need to work more on, and also dynamic fusion, right? So we don't just want to move the points from one frame to the other. We also want to fuse the past observations into the current for dynamic part of the scene to make it more complete. And second, modeling context is still a very challenging topic, and how can we make this method work on longer sequence than just a few hundreds of frames is an open challenge. And lastly, as I mentioned before, this method still requires supervised training data, and if we can unlock unlabeled video data, that will be a very exciting direction to explore. Okay, thank you to my collaborators, and thank you for listening.